Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to discuss the issue of non-stationarity and look at some of the equations we've seen more in depth. This will be useful for later lectures, since the same equations are going to show up again and again. So what do we mean by non-stationarity? A stationary process is a process whose statistics don't change over time. We are interested in the mean, but strictly speaking, there are different types of stationarity. Weak sense stationarity is when the mean and autocovariance don't change over time. The autocovariance is a second-order statistic. There is also strong sense stationarity, where the entire PDF has to remain the same over time. This is the kind of stationary that we have, because each bandit has the same distribution each time you pull its arm. Note that a strong sense stationary process is also a weak sense stationary process, but the reverse is not true. The question is, what if the bandits weren't stationary? Would it then make sense to calculate the mean as we have been? Recall our mean update equation from earlier. Let's call x bar q for convenience. We can rearrange the terms so that we have the 1 over t term all by itself. We can generalize this even further so that the 1 over t term is represented by a learning rate alpha, so it kind of looks like gradient descent. The key with this equation is we don't have to use alpha equals 1 over t as the learning rate. If you recall from Deep Learning Part 2, a 1 over t learning rate was only one of the adaptive learning rate techniques we studied. But learning rates can be anything. What if we set alpha to a constant? This equation should look familiar too. This is something we looked at when we were looking at simple examples of how to use the Theano-scan function. Recall that this implements a simple low-pass filter. If we get rid of the recurrence, we can find q in terms of all the pass values of x. And from this we can see that q has an exponentially decaying dependence on x. In this way, q puts more emphasis on recent values of x rather than past values of x, so it's like a moving average, or in other words, low-pass filter. If you want to run the low-pass filter from the Theano-scan tutorial, the relevant folder is HMM class and the relevant file is scan3.py. You can see here that we start out with a very noisy sine wave, and after we pass it through the low-pass filter, most of the high-frequency noise goes away. There is a popular result you usually see in reinforcement learning literature that talks about the convergence of Q. The result is that Q will converge if the sum of all alphas is infinity, but the sum of all the squares of the alphas is constant. If you think back to Calculus 2, it should be clear from these criteria that constant alpha does not meet these two conditions, but alpha equals 1 over t does. The reason you often see a constant alpha used is because reinforcement learning problems are often non-stationary. So it doesn't make sense to try and calculate a sample mean over every collected sample ever. Let's do some simple problems to solidify this concept. We already know that 1 over t converges, but what about 1 over t squared? If you want to pause the video and think about it, please do so now. So this doesn't converge because the sum over all alphas is not infinity. What about alpha equals 1 over t to the 2/3? If you want to pause this video and think about it, please do so now. In this case, there will be convergence because the sum over all alphas is infinity. But if we square alpha, the power in the denominator becomes bigger than 1, so that converges to a constant.